It's a great pleasure for me to welcome Andrei back to Stanford. So Andrei is a pride of Stanford. He grew up in Romania, and he participated twice in the Olympic physics competition, and twice won the Olympic gold medal. It was at a time when he was applying for undergraduate school. The distinguished colleague, Dr. called him personally and recruited him to Stanford as an undergraduate student. So he he majored in physics, and he did his undergraduate thesis with our distinguished colleague Bob. And afterwards, he tried to go to a different school for graduate school, and he was at MIT. But I remember once we bumped into each other at the elevator and told him a little bit about what I was doing, and a few weeks later, he switched to Stanford. So we had really a tremendous fun, a period when topological physics in comprised matter was just picking up. And I still remember in year 2005 and 2006, we wrote a series of papers culminating in the prediction of the first topological insulator in mercury telluride with another student, Taylor Hughes. So then he became a postdoc at Princeton, and very soon was appointed to be a professor and now a full professor at Princeton.
Long time.
And we actually held living in suspicion. We don't know what he's going to do next. Very soon you will find out by reading the news. But anyhow, so he has been leading the charge in developing this exciting field of topological comprised matter physics and at the intersection of material science. And this is the cover page of Nature that you are seeing, and this is the exciting work he will share with us today.
Thank you very much, Sushang, and everyone. Thank you for coming. It's kind of an emotional time to, as I was walking to Tresidder for lunch. Nothing has changed in Tresidder, by the way. Not even the quality of the food. But it was still an emotional time, and kind of like, I guess, if I was to say something about that, of course, I would have only nice things to say, but if there was something to say is that if I had to do it all over again, I would do the same thing all over again. So I guess that's the best thing to say, in my view. Okay, so what I'm going to talk to you about today is kind of give you an overview of what happened in the past 12 years in this field that Sushang mentioned of topological insulators and topological materials, to which Stanford has been at the forefront of developing, and to show you where the field, well, part of the field is going, and mainly to, in the end, to relate this field to the discovery of new materials with topological properties in a way that can be automized and checked, and where predictions can be made. So basically to kind of go the full gambit from predicting topological phenomena to predicting materials in which they will develop and to be right about it. So the field of topology, yes?
Was that image, was that a PowerPoint image, or is somebody made a statue like that?
No. This will soon be in the next to the Trump Tower. The Nature graphic designer made it.
I see.
But it was an idea of Claudia Felser and myself as we were sitting in an airplane waiting to take off to put. Anyways, so and it will not be in front of Trump Tower. Hopefully. Okay, so this field of topological matter, as I said, is, to me at least, very, very interesting because it involves unique collaboration between seemingly disconnected branches of physics, mathematics, material growth, quantum chemistry, and quantum materials. But before we kind of get into it, basically I want to sort of give you an overview of what topology has to do with physics, and especially with real properties of real materials. So if you go into the Wikipedia and type in topology or topological order or just topology, the field of mathematics, you get the following definition, that the topology is the area of mathematics that deals with properties of manifolds invariant under smooth continuous deformations. And then you go on Google and try to get some image for a colloquium, and you get this image, where you have different manifolds that are not connectable to each other in a smooth fashion. And the reason for that is obvious, as everybody knows here, that in order to go in between all these manifolds, I need to drill holes in them, and that's what you define as a non-smooth deformation of a manifold. So basically, you have different ways of classifying them in these categories. It's just the genus, or the number of holes in the surface, and this is a sphere, a donut, a two-handled cup, and etc. And this is a Swedish cup, I guess, or something. So, but they're all non-deformable to each other. So what does this have with the following field, in which Stanford had, obviously a very powerful presence, the field of electronic bands. So if I take electrons, non-interacting electrons, and put them in a periodic potential, by now there's codes to deal with that, to find the allowed energy states of electrons in periodic potentials. And the output of a code would give you something that would look, if you're lucky, like this. Most of the times it would look like a spaghetti, much more awful than this, a spaghetti of bands. But sometimes it can look as nice as, the bands of silicon. These are allowed energy states of the electrons. And here there's a disallowed energy state of electrons, which is a gap, etc. But you can kind of get, if you have a good code, a one-to-one correspondence between the material. The code calculates some values in the material orbitals, etc., and outputs this band diagram. Now, if you look closer to this band diagram, it's got several properties that you might want to explain that are not. They don't seem to be quantitative. So, for example, one property is that as you move around in these electron-allowed band structures, you kind of go through degeneracy points, and then you go through what we call, I will call in this talk connectivity. So, for example, here you can see that there's three sets of bands that cannot be disconnected from each other, for example, because they've got the degeneracy here and degeneracy here. Degeneracies don't need to happen at high symmetry points, but basically you can kind of see that because of degeneracies here, this set of three disconnected bands cannot be kind of separated apart. If I pull them apart, they're kind of like strings that are connected at some point. And these bands too, also, you can see that there's, for example, this is not an avoided crossing. This is a real crossing. You can see some things that kind of need explaining in this set of bands. I'll argue that this has to do with topology, but even more at a more basic level than that, there is a connection between bands or wave functions of electrons and topology. And this connection has to do with basically, in the simplest case, with the Briand zone. So the simplest way to explain why topology comes into physics is to think about, again, band theory and plane waves of electrons. And if I have a lattice that has no disorder, that's just translation invariant, what I can do is, instead of looking at a Hamiltonian or a Hamiltonian of electrons that has some hopping between electron on this orbital and the electron on this orbital, adjacent to it, etc., which is obviously not diagonal because I have different spaces. This is one Hilbert space, this is another Hilbert space, so I hop from here to here. I will need to do what's called a Fourier transform and go to the Briand zone. So from just the real lattice, I go to the Briand zone. And in this, if I have a single particle Hamiltonian in this Briand zone, which is basically the momentum space, it's basically this what I was plotting the energy of the electron versus. In this momentum space, the Hamiltonian becomes diagonal. And now, since it became diagonal, I only have to solve a much smaller problem, which is the problem of the orbitals in a unit cell, in what's repeated in the lattice. So this is basically the Fourier transform. It's a canonical transformation. But Felix Bloch basically, showed that once you Fourier transform to the momentum space, your Hamiltonian becomes periodic with the reciprocal lattice vectors. Okay, so the Hamiltonian of the electron at momentum k is the same up to a unitary transformation as the Hamiltonian of the momentum of the electron at momentum k plus a reciprocal lattice vector. And this makes the momentum be a d-dimensional torus in d dimensions. Now, of course, in order to get the properties of materials, I have to compute the electron wave functions. And when I compute the electron wave functions, all I'm doing is I'm solving a Schrodinger equation. So this is the equation that I'm solving. And this was kind of the insight of Felix Bloch, this Bloch periodicity, etc., of electrons in the Brillouin zone. But the new insight, which really started in the 80s and continued with adding symmetries in 2005, 2006, is the fact that these wave functions by themselves actually are important, and not only that they're solutions to the Schrödinger equation, but they hold topological properties. So let's see how they do this. Well, the simplest example to see this in is the example of S&P orbitals. If I sit on a site and I have S&P orbitals on site, okay, then my electron has the probability of sitting in the s orbital and in the p orbital. And these are the probabilities psi1 and psi2 of the wave function. I'm forgetting about spin. So psi1 is the probability of the electron to sit in the s orbital, psi2 is the probability of the electron to sit in the p orbital, and they vary, they're depending on momentum, as I move momentum in the Brillouin zone. But because the wave function is a spinner, it itself defines a space, and this, in this case, is a two-sphere. And the way you can see that it's a two-sphere is, you know that each of these two numbers can be a complex number, psi1 and psi2, it's just a wave function probability. But you know that this equation has what's called a U1 degree of freedom in the sense that I can multiply this Hamiltonian, which is a 2x2 matrix in this case, by a U1 gauge transformation, like just a phase factor, to the left, on the left-hand side and on the right-hand side. And I wouldn't change, I would still obtain the solution of the Schrödinger equation. So what I can do by doing this is make this psi1 real. Okay, so I can tune at every k the phase to make this psi1 real. I make this psi1 real and this psi2 imaginary. So I have three components. One, the real part of this, the only part, and the real and imaginary part of this. But this wave function is subject to a normalization constraint. It's got to have modulus 1. So that gives you, real part of this squared plus real part of this squared plus imaginary part of this squared equals to 1. That's a two-sphere. So we just established that these wave functions really are maps between a torus in 2 dimensions, let's choose it 2-dimensional here, and a two-sphere in the case of S&P orbitals. In the general case of having more orbitals, there are maps between the torus and the complex projective plane, but that we won't get into those details. The point is these maps, these wave functions, you can now think of them as maps between some Brillouin zone and some space that's defined by your orbitals that are sitting on the lattice. So if I think of them, of the wave function as maps, then I can go to the field of mathematics called topology and give these maps what's called topological number. So basically define these maps by some properties that cannot be changed smoothly. And the simplest way to see this is the following. For example, if a wave function is defined as this map from the torus to the two-sphere of S&P orbitals, and if the wave function just sits at the north pole, so in this case would be psi, which had the two components, psi1 and psi2, is just equal to psi1 and 0, or 1 and 0, so psi1 would be 1. That means that my wave function of the s orbital is fully occupied. My system sits only on the s orbital. Every electron on every site sits in the s orbital. That's an insulator in the atomic limit. Okay, and the electron sits just in the s orbital. If, this would happen if the Hamiltonian of the s orbital, if the on-site energy of the s orbital would have been negative infinity. It wouldn't matter if I would have hoppings. My wave function would just sit in this case. Well, obviously, if it sits just at the north pole, it means that as I move the momentum in the Brillouin zone, the two torus, this wave function covers a whole of 0 of this sphere that it maps into. It just covers this point. The fundamentally different situation is the situation where, and I haven't showed you the Hamiltonian for that, but you can build simple Hamiltonians for that, where the wave function, as I move this momentum k on the two torus of the Brillouin zone, covers the full sphere S2. So there's no point in the sphere that's left uncovered as I move this k onto the Brillouin zone. And that's called the topological number 1. And the fundamental moral of the story is that there's no way to go between 1 and 0 by adding infinitesimal integers. So if there's no way to, by adding 10 to the minus infinity. So there's no way to go from here to here, from between two integers by adding infinitesimal numbers. So there's no adiabatic evolution between maps or wave functions that have the covering the topological number 0 and maps that have a topological number 1. These are two disconnected subspaces. And the only way to go from here to here would be to close a gap if in the Hamiltonian space. Then that's the physical interpretation to go from here to here. But there's no way to adiabatically go from here to here or to add infinitesimal integers to go from 0 to 1. Now, I've shown to you that there's two kinds of maps. Okay, and you can now imagine that there might be maps that cover the sphere 2 times or 3 times, etc. And we'll get to that. But there's two kinds of maps, and since maps are wave functions, and wave functions classify materials, it's pretty easy to believe now that topology comes into play, that the topological numbers, or the covering number of this sphere as the torus moves, as the momentum moves around the torus, comes into play in the properties of materials. So let's see how it comes into play in the properties of materials. Well, if I have two insulators with different topological numbers, the first thing you can say immediately just by thinking about things without any calculation is that there have to be Gapless Air states between them. And why? Well, what I can imagine as a thought experiment is this kind of situation, where this is an insulator that's described by SMP orbitals, my previous model, where the wave function has a topological number, so the covering of the sphere, which is 0. So imagine that the wave function was sitting right at the North Pole, as in the first example of my topological number 0, of covering number 0. And I'm adding next to it what I call a nontrivial insulator, or an insulator that cannot be adiabatically continued to this guy, that's got a wave function which is described by a covering of this sphere, which is equal to 1. Well, if I make this system large, like if I go take the system to the Andromeda galaxy and this system to the Milky Way, then of course in the bulks of the system, I've broken here translational invariance, so you can accuse me that I cannot Fourier transform anymore. But of course here I can still Fourier transform, and here I can still Fourier transform. I can basically have translational invariance over some distances if I make this bulk huge. So the moral of the story is that these phases are still distinct, and there's no way to get from one phase with a wave function describing one topological number to another phase without adiabatically or by infinitesimal transformation, without closing the gap or without having a region of gapless edge modes. Where this region of gapless edge modes sits is something quantitative that depends on parameters, but the moral of the story is that there always has to be a region of gapless modes that interpolates between two insulators described by maps with different topological numbers, or by wave functions with different topological numbers. And the other moral of the story is whatever I do to this region of gapless modes, so for example I take a hammer and hit here, this region of gapless modes would just move in and move into more if I hit with a hammer more, but you can never get rid of it, right? So they're kind of very protected. They form a gapless liquid that's stable. Okay, so I've told you now that topology matters. I've showed you the physical consequences of what topology gives you. It gives you the edge states, which you can measure. And now I'm going to tell you how many types of topology you can have. And it turns out you can find out how many types of topology you can have just by drawing pictures. And the pictures that we're going to draw are going to be in 2 dimensions, but in a weird geometry that's colloquially sort of referred to as the Laughlin Cylinder. And this geometry is periodic boundary conditions in one direction, just to exploit the symmetry that we still have in the system, or potentially have in the system, and open boundary conditions in the other direction. So the strategy will be draw band structures with block periodicity in the k direction, the only k direction, and see how many band structures you can draw. Well, I can certainly draw the trivial band structure where I have electrons sitting in bands that here look filled. The reason why they look filled with states is because I put open boundary conditions in the x direction. So the number of states I'll have here is equal to the number of orbitals times the number of sites that I have in this direction. That's the number of states that I'll have at each k. But you can see that I have what's called a bulk gap, or a region of forbidden electron states that sits here. I can certainly draw this picture, so hence it has to exist. But I can draw the other picture, or another picture, that is more interesting. And this picture has to do with drawing what's called the region of edge states in between the valence and the conduction band. So if I draw a region of states that doesn't look, like it's a region of bulk states, because there's only very few states here. There's no large region of density of states in the gap. If I draw an electron band that interpolates between the valence band and the conduction band, and I'm just drawing one set of bands on one edge, there's a set of bands on the other edge that I'm not drawing, that goes in the opposite direction, then this satisfies block periodicity. And if it's connected to the valence band here and to the conduction band here, then it can never be broken up. So what you can do is just add some impurity on the edge and move this down a little bit or move this up a little bit. But the flow, the fact that it flows in one direction, can never be broken. And this is, of course, the quantum Hall effect. And this number of edge states here is 1. And it turns out that this Hamiltonian of this state in the bulk is described by a wave function that's a map with a topological number 1. Now, of course, I have 2 edge states on the same edge, or 3 edge states on the same edge, and then I will draw 3 chiral modes here, or 2 chiral modes here, and those will be different types of insulators. So all of this is, of course, known to people here. This is just, the work that basically got several Nobel Prizes in condensed matter. And the new work that basically started with 2005 when 2006 is adding symmetries to the system. So far, notice that I haven't talked anything about symmetries except for translational invariance. I've just been saying, well, in translational invariances, I've only needed it really. I can't go through it now, but I've only needed it in order to make things simple to understand. Now, it turns out that if you add symmetries to the system, and the simplest symmetry you can add is time reversal, then you can stabilize a new set of topological states of matter. So a new set of insulators that are completely disconnected from trivial insulators. And let's go through it. And this is, of course, the time reversal invariant topological insulators. So why is time reversal important? Well, time reversal is important because it again allows you to draw edge states that are stable. So I argue that the only thing you need to know to understand topological insulators is to be able to draw states, but now I have another thing that I'm imposing on the system, which is a symmetry. So time reversal is a symmetry that takes s to minus s, spin to minus spin, but spin 1/2 is somehow special, and the reason why it's special is because when I make a 2 pi rotation of a spin 1/2, this gives me a -1. So what that means really is Kramer's theorem. It means that you actually have states coming in double degeneracy at some momentas in the Briand zone. I'll explain all this in a minute. But for the matter of this slide, just consider the same geometry of the cylinder with open boundary conditions in this direction, periodic boundary conditions in this direction. And here I'm trying to write down all the possible insulating band structures that have time reversal. So the first one I can write is, of course, the trivial band insulator. Or the first one I can draw is the trivial band insulator. This is a state of, these states are filled here. These are bulk states with a band gap in the bulk where electrons cannot sit. Now, in order to draw more band structures, I'm going to particularize to a color coding in which spin up is red, spin down is green. And time reversal changes spin up into spin down. So, for example, I can write down, or I can draw this type of band structure where you can immediately imagine that you can have 0 to 2 pi periodicity just by drawing it. You can have 0 to 2 pi periodicity. I can draw this band structure where I have bulk bands, spin up moving chiral at some momentum here, spin down moving antichiral at some momentum here, spin down moving antichiral at some momentum here, and this is given by time reversal, because if I have a spin up moving chiral at some momentum, I must have a spin down moving chiral at minus that momentum by time reversal. Time reversal also flips momentum, and vice versa for spin up here and spin down here. So this respects time reversal. If you think this is 0 or pi, This is the zero momentum in the Briand zone, respect time reversal. And you can argue, well, you know, this is a band structure that I can draw, hence it exists. Well, yes, it exists, but the problem is that if I have spin-orbit coupling, spin up and down are not good quantum numbers anymore. So what happens is that I can gap these states here by just putting some impurities, by making some spin-orbit coupling impurity, as long as I gap the states at minus k. So this is a perfectly time-reversal invariant gap that I can add in the system. Okay? I can add in the system. And once I gap it, I can tune up that impurity and make this look like this. Now the moral of the story is that if I have just one set of what's called helical edge states, so one moving in one direction, spin up and spin down moving in the opposite direction, rather than two, like here, this I cannot gap. And this I cannot gap because time reversal at momentum 0, where these states have to touch if I have only one pair of them, time reversal changes spin up into spin down. So in order to gap them here, it would mean a term that breaks time reversal. They basically flip spin up into spin down at the same momentum. Here I could do it because this time reversal relates this momentum with this momentum. Here I cannot do it without breaking time reversal. So it turns out that this situation is stable. This situation is not stable. This is equal to this. This is not equal to this. Hence you can clearly see a Z2 type structure. One pair of edge states is non-trivial. Two pairs of edge states is trivial. Okay, so this is, you know, the past, until I guess 2015. This was mostly the name of the game and led to all these discoveries of what I think are kind of remarkable phenomena in condensed matter and the quantum spin Hall state in mercury telluride. A lot of 3D topological insulators and monopoles and dislocations, modes on dislocations, etc. So basically a kind of a regeneration, a new revolution I would think, in condensed matter of adding time reversal and particle Hall with superconductivity on topological systems and finding how many disconnected types of insulators do you have. Now, in 2000, so far I've talked only about insulators, but in 2015, people have discovered the first, or have predicted the first topological semimetal. So it turns out that if you take the Dirac equation, so this is called the Weil semimetal, which also exists because of topological properties, and is related to looking at the Dirac equation and making its mass equal to 0. So the Dirac equation is a 4x4 equation that I learned from Renata in my quantum field theory class here. And the fundamental thing that she impressed upon us was that it's got plus and minus signs here. If it didn't have plus and minus signs here, then you couldn't gap the Dirac Hamiltonian. Okay? If the signs were both plus. So that basically tells you that if I make the mass 0, okay, I can write a consistent equation for half of the block in a Dirac equation. And this half of the block is called Weil fermion. And there's another Weil fermion with a minus sign here, which we'll come to it in the next slide, which is also exists in this equation. Now, Weil fermions, they've been trying, people in high energy have been trying to discover them. All fermions at high energies are supposed to be Weil, but as you lower the scale, they acquire a mass. But in condensed matter, they're very easy to find. Why? Because half of this Weil, half of the Dirac fermion, which is a Weil fermion, you can just think of it as a band crossing between two bands. It's a 2x2 subspace. It's got two bands, and it's got a band crossing. So again, now we're talking about band crossings in the bulk, so metals in the bulk. We switch from insulators. So it's got a band crossing in the bulk, and around the crossing point of two bands, I can just describe my Hamiltonian as in some basis, it has to be a 2x2 Hamiltonian, it has to be expandable in these matrices. The crossing point is at kx equals ky equals kz equals 0 at around some point in the Briand zone. And now I can ask, well, can I do anything to this Hamiltonian? Can I do anything to this Hamiltonian, which is obviously a metal, because the dispersion relation looks like this, okay, at kz equals 0, and whatever you do to this Hamiltonian, to this particular Hamiltonian, at half filling, it would be a semi-metal. You can ask, can I do anything to gap it? And the only thing you can do is add terms. You can just play around and add terms to this Hamiltonian. The first term I can add, for example, is a mass term, and I pick which mass to add in which matrices. And you discover that if you pick any mass that you can add to this Hamiltonian in any matrix, so I pick a mass times sigma x, all I've done is I've moved this degeneracy point, which existed at kx equals ky equals kz equals 0, I've moved it to kx equals m, ky equals 0, kz equals to 0. So all I've done is, instead of gapping this point, I've just moved it around in the Brillouin zone. So this is why these things are called semimetals, topological semimetals. What you can do is move the gapless points around, but you can never gap them, at least in single particle, and actually it turns out even with interactions because of density of states arguments. And these are not the only 4 equations in the talk, but they're quite kind of revealing. In fact, if you look at this Weil Hamiltonian, and you take this, k dot sigma, kx sigma s plus ky sigma I plus kz sigma z Hamiltonian, you plug it into Mathematica, you solve a 2x2 problem to obtain its eigenstates. What you can do is solve what's called this is called the Berry connection. It's just a very simple, vector potential. Then you can take its curl, kind of like you do in electrodynamics, taking the curl of A to obtain a magnetic field. It's just a magnetic field in momentum space. And you find out that this curl has the form of a monopole. The monopole sits at the gapless point of this Weil fermion. And in fact, if you were to plot the wave function configuration of this wave function as the momentum now goes around the Fermi surface, you'd find out that it covers the Fermi surface exactly once. So the mapping number of this, the covering number of this wave function that I've talked at the beginning is exactly that example that I gave at the beginning. It's once. Now, in condensed matter, if I've got a monopole at k equals 0, we know that, well, not in condensed matter, we know in condensed matter and high energy, we know there's got to have a Dirac string coming out of it. In high energy, they don't have a bandwidth. They take this Dirac string to infinity. In condensed matter, we have a bandwidth, so we take this Dirac string to end in another monopole. So monopoles in condensed matter, or Weil or gapless nodes, come in pairs. And you can ask, is there any physical significance to this Dirac string? Normally it's kind of a gauge transformed. You can gauge transform it around. You can't get rid of it. You can ask, is there a physical significance to this Dirac string that goes in between one gapless point and another one in the lattice? And the answer is yes. And this is the answer. Just forget about the left side. The answer is that if I have 2 Weil points, then they always have to come in pairs, as I said, because they always have to have a string coming out of them has to end in another one in condensed matter. If I have Weil points in the bulk and I look down on the sample like this, on the surface of the sample there are what's called Fermi arc states, so kind of unclosed Fermi surfaces, closing the connection between the Weil points projection to the surface. So if I had the Weil point in the bulk, I have a 3D sample, I have a Weil point in the bulk here, a Weil point here, I look on the surface, I project this Weil point to the surface, project in the bulk of the sample is gapped at this momentum on the surface. It's only gapless here and here at 2 points. But on the surface of the sample, I have this Fermi arc, which is an open Fermi surface. Now, of course, the closure of this Fermi surface happens on the lower surface. This is kind of a remarkable phenomena that tells you that basically this open Fermi arc here is seeing the Dirac string in that's going in between these 2 Weil counts. It's basically the physical manifestation of the Dirac string. Here you have many of them, just because there's more Weil points that project to the same one. But basically, if you look here, there's a Weil point here, there's a Weil point here, and you have 2 Fermi arcs. Just because this is a more complicated material, you have 2 Weil points that project. But you can clearly see this is an ARPES experiment where you can clearly see what's the significance of having these topological gapless points in the bulk of the sample. Okay, so I've sort of gone in, I hope only 25 minutes, through a a short history of what happened in the past 15 years. And I've skipped, so this history in the past 12 years, I guess. We're growing old. So the quantum spin Hall, the Dirac, the 3D topological insulators, the Fermi arcs, and what I skipped is important contributions in when you add superconductivity that have to do with Majorana bound states and chiral Majorana fermions that are very important to quantum computing, etc. But it turns out that that's only a small part of band topology. Why? Because we've only spoken about time reversal. So you can ask, well, are there any other symmetries that kind of disconnect the space of insulators and the space of semimetals even more? Can you ask, well, if I add mirror symmetry and I really make sure that my sample has, I don't put more disorder on one side, even disorder, I make sure that on average respects mirror symmetry, can I have more topological classes? And it turns out that the answer is yes. You can have something that looks like this on the surface, for example, like an hourglass. And this is protected by what's called the Glide symmetry. This is more complicated. Or you can ask, can I have more semimetals rather than this nodal line semimetal? And it turns out that you can have things that look like nested loops where the gapless region of points in the bulk connect at points. You can have all kinds of crazy things in bulk topology. And the way to find materials for these type of topologies or for these type of topologies was previously unknown, or how to even classify all types of topologies. So now I'm going to tell you how to do it in the remaining time, how to classify all types of topologies and how to predict materials and how to check that you have materials. And I'm going to give you the website where you can go and check if you have a material. And for the purpose of this discussion, I'm going to say that something is interesting if it's got edge states in the bulk gap when you open the boundary on one surface, if it's an insulator. So this is interesting, this is boring. And if it's a semimetal at half filling, for example, this is interesting because I have a node here that is protected, I can not get rid of. Whereas this is boring because by just transforming this, taking this and moving it down, and taking this and moving it up, I can make this metal be an insulator. I'm just going to take this part, move it up, take this part, moving down. I still maintain half filling, but this is topologically boring, whereas this is topologically interesting. This is just boring and interesting in the eye of the beholder. This is topologically, this topological classification of boring and interesting. Okay, so the question that we're going to ask is how do you obtain the full space of topological systems, at least for non-magnetic groups. For magnetic groups, there's a harder classification. And how do you predict materials that would have the type of topology or new types of topology that you want? And the inputs should not be more than the inputs that you get in the international database of materials. And these inputs are the stoichiometric material structure and the set of orbitals or atoms and where they sit on the lattice. If you have the material structure, you also have the space group, you also have the X-ray diffraction in the material database. So you know the full space group of the lattice. And you also know the Wyckoff positions or where the atoms sit on the lattice. And this is all I'm going to require to be able to provide some sort of a classification of the systems. So now, in order to ask, how do we get topological bands, we should first ask, well, what is a band? So now we're going back to the first slide. So what is really a band? And I don't want to think about Hamiltonians anymore. The reason why I don't want to think about Hamiltonians anymore is because I want to obtain a theory that's qualitative that will tell me basically what types of different bands I can have and whether they can be topological, irrespective of the details of the Hamiltonian, the first nearest neighbor hopping, the second nearest neighbor hopping. So the building blocks of the theory are what's called elementary band representations. And these were started by Zach, Bakri, and Michel. And actually there's many works by Wigner and Herring that are kind of leading on to what these guys built. And In the 1990s, or early 2000, 2001, they stopped writing papers because Bakary and Michel died early 2000s. These three people were very close to obtaining topological insulators in 2001. They basically didn't obtain topological insulators because they didn't check 2 more cases of what I'm going to tell you. Okay, so we're going to just ask what are bands and what are elementary band representations, which I'm going to tell you what they are. So what Zach said is, how do you build a band without a Hamiltonian? Well, you have an orbital arrangement. You have some orbitals sitting on lattices, and they must be consistent with space group symmetry. So let's take the graphene example, which is the easiest example, and I'm going to consider one lattice site. This is the A sublattice of graphene, say. And even though the space group of or the point group of the graphene lattice C6, you can see I can do a 6-fold rotation. The symmetry group of this site, if I put my orbital C6V, so I can do a 6-fold rotation around this point and some mirrors around this line and around this line. That's the point group of the graphene lattice. This is not the point group of an atom sitting at this position. The point group that leaves an atom sitting at this position invariant is called a site symmetry group, is GQ, and it leaves this Q invariant. And you can clearly see here that is C3 on the graphene lattice, just because this lattice site sits here. Is C3 plus this V just tells you that you have mirrors. So you have this mirror, this mirror around this axis. So this C3 leaves this site invariant. So any atom that I put there, or any orbital that I put there, has to transform under representation of this site symmetry group. So for example, PZ orbitals in graphene transform without spin as a one-dimensional representation of G of C3V. Now you can ask, well, my point group of the lattice, of the graphene lattice, is much larger than, well, it's not much larger, but it's larger than C3V. It's C6V. Okay? So what does C6V do? Well, C6V has one element that's not in C3V, and that's the C6 rotation. And of course, we all know what it does, is it takes the A sublattice site of graphene and moves it into B. And this is how you build your unit cell. Okay? So now comes the fundamental insight of what bands that are obtained from orbitals are. So Zach said, well, okay, well, I know that I have these orbitals on, one lattice site here in the A lattice or A or B lattice site of graphene. Okay? But I know that C6 must tell me the element that doesn't sit in the stabilizer or C3V group that leaves this site invariant. C6 moves it here. Okay? So I know my unit cell has 2 sites. And then now I have to implement translations. So that's a much larger group. That's the space group. I started from a point group here. I'm implementing the full space group by first implementing a unit cell and then translating the unit cell around the lattice. Okay? So you define a band as the collection of all symmetry-related orbitals that appear once you take the site symmetry group here, a representation of this site symmetry group, translate it in unit cell, and then translate it everywhere in the lattice. And there's a way to do this, which is called representation induction. So the moral of the story is that you define bands as representations. And this is a fundamental insight because it allows you to get rid of Hamiltonians. Well, up until you want to check things. But to define things, it allows you to get rid of Hamiltonians. So representation induction is something that was defined by Frobenius. Frobenius was trying to obtain representations of large groups, but he only knew representations of smaller groups. So he said, well, is there a way to obtain representation of large groups from smaller groups? Well, yes. What you do is representation induction. There's a formula for it. You can do it. Now, we want to do the same thing. We have a small group, which is the point group of this lattice site where I put my orbitals. And I want to obtain a band. Well, I'm going to define the band as the induced representation of this orbital here to first the unit cell, so I have another orbital here, and then all the space group. The space group is a much larger group than the point group. Okay, so this we're going to call representation induction. This row is a representation of the orbital on this side. Since this is a point group, this is a finite number of representations. I'm inducing to the full space group, and this I call a band. And now the point is, once you are thinking of bands as representations, you can ask questions about their reducibility. So normally we want to know if a representation is reducible or irreducible. I can ask the same things about a band. And now come two fundamental theorems. Well, I'm not going to, there's a lot of math going around these things. I'm not going to talk about it, but the fundamental thing, there's two things. Well, you know, if I put orbitals here, I told you that they sit in a representation of C3v. Now you can ask me, well, C3v has many representations. And I can say yes, but only few of them are irreducible. And it turns out that in order to obtain an irreducible band representation, which I'm going to call from now on elementary band representation, that's the irreducible kind of lingo for bands, the only thing you need to consider is the irreducible representation of the site symmetry group. And those are very few, okay, because site symmetry group is a point group. So whatever orbitals, you know, if you tell me, when you tell me P, D, F, whatever orbitals, those are an infinite number of orbitals of the SO3 symmetry group. But once you've broken the symmetries to point group, all of those fall into a finite number of irreducible representations of those orbitals. And these are the only types of representations you need to consider here to think of, to find bands. The next thing you can tell me is, well, yes, but I can put my atoms anywhere on this lattice. I can put them here, I can put them here, I can put them here, I can, you know, or the center of charge being quantum mechanical, even if I put my atoms here, for example, graphene has what's called sp2 hybridization for the occupied valence band. So actually the center of charge for the occupied valence band sits here. So you can ask me, well, you know, even though I put my atom somewhere, the center of charge can sit anywhere else. And what you can actually prove is that what's called only the maximal Wyckoff positions, or only some parts of site symmetry, some sites matter. So for example, in graphene, only these three types of sites matter. So in the sense that I can obtain all the elementary band representations from orbitals at these sites. This site, which has got 2b, which site symmetry group C3v, these are the A and B sublattices of graphene. Okay, there's 2 sites per unit cell. 3c, there's 3 sites per unit cell, and 1a, which is the triangular lattice. Really, if you put atoms here. So in order to find how many bands you can have, how many types of bands you can have in a system for this space group, the only thing you need to know is the irreducible representations of the site symmetry group of 2b, which is C3v, 3c, which is C2v, and 1a, which is C6v. That's the only thing you need to know. And you can do some theory, and you can basically complete the program that was initiated by some groups, by Zach and Becker and Michel. So it turns out that there's 10,000 elementary band representations, and I'll tell you why they're important. But first, let me give you a rough idea of why there's 10,000. There's 230 space groups. Out of 230 space groups, you know, they have each of them, say, 5 positions that are important, 5 positions in the lattice that are important, and these positions are classified by the fact that they have maximal site symmetry group, which I don't want to get into. There's just around 5 positions that are important here. There's only 3, these, this, and this. And for each position, there's about, say, another 10 representations. So that's 5 times 230 times 10, around 10,000 such representations. They are now all tabulated on a website. Okay, so what did you get? What did you gain by having these bands? Well, what you've gained is actually a lot. We now have a way of getting from orbitals sitting on lattice sites up into the full space group to obtain a band. I can now Fourier transform this band. I can now go to the Briand zone, and for this band, I know every representations at high symmetry points. So what you do mathematically is called representation induction. I go from the site symmetry group to the full space group to the point group of high symmetry points in the Briand zone. So you know all the eigenvalues of these bands at high symmetry points just by a simple computer code. And even more, the other thing that you know that's not easy to understand is the following. Since my space group is infinite, it not only contains eigenvalues, but it contains what's called, fiber bundles, which is really Berry phases. It contains parallel transport. So you know all the Berry phases of these things just by inducing the representations, all the Berry phases of these bands. Even though you don't know anything about energy. So in other words, you don't know where this point sits, but you know this in this band that's I obtained from, say, pz orbitals of graphene on the A sublattice, on the A position, I should get some representations at the gamma point, some representations at the K point, some representations at the M point. Okay, so now why are elementary band representations important? So I've told you how to get them, but why are they important? And why did Zach, Bakri, and Michel fail to get topological insulators? Okay, so Zach, Bakri, and Michel had a paper called Elementary Band Representations Are All Connected, which means the following. It means if I take one orbital at a site symmetry group and I induce from this orbital a band, okay, and this band is elementary, and we have a way of getting this 10,000 elementary bands, then these bands are all connected in the Brillouin zone. So for example, a set of orbitals induces all connected bands in the Brillouin zone. And this is what really means in the Brillouin zone to be an irreducible band representation on elementary band representations. Normally when I have irreducible representations in group theory, it just tells me that they're stuck together in energy at some high symmetry point, etc. To have an elementary band representation is just telling you it's stuck together in the Brillouin zone. Okay? So Zach, Bakri, and Michel basically said that if I induce from some orbitals at some lattice site in the Brillouin zone, I obtain connected bands in the Brillouin zone. If I induce from some set of orbitals on a lattice site, I obtain connected bands in the Brillouin zone. Now they based this on checking several groups. They checked about 10 symmetry groups without time reversal and without spin. If they had checked another 10 groups, they would have found that there are elementary band representations that come disconnected. And the reason for that is topological insulators exist. So why is this? Well, topological insulators are defined, there's another definition that we cannot explain mathematically, but we can believe, are defined as insulators that cannot be obtained by localized atomic orbitals. Why? Well, if I had a topological insulator that could be obtained by localized atomic orbitals, so this would be exponential, and I'll put it next to a trivial insulator, which by definition is obtained by localized atomic orbitals, my S, then there couldn't be any set of extended edge states in between them, because extended edge states are not localized, they're not exponentially localized. So by definition, a topological insulator cannot be described by a set of maximally localized orbitals. Now, by construction, all our elementary band representations, or all these things that we constructed, we're just constructing from atomic limits, from orbitals on site. So by construction, these 10,000 things that we constructed are just all the atomic limits. Okay? So anything that's not an atomic limit cannot be described as induced from a set of orbitals from some points on a lattice, from maximally localized orbitals, and hence is not an elementary band representation. So that's the definition of topological, the encompassing definition of topology in band structures. The definition of a topological band is a band that's not continuable to a sum of elementary band representations. And now, since you have all the band representations in all the space groups, you can check if a band that you get in ab initio from some calculation is a sum of all these atomic limits. If it's not, it has to be topological. Okay, how much more time do I have?
5 minutes.
Okay. But moreover, you can also predict how many bands are not obtained from maximally localized orbitals. And how can you predict this? Well, the way you can predict this is by working purely in momentum space. So what we have is all the bands that can be obtained from localized orbitals sitting in real space. We have their structure in K-space, but we can just work in K-space and ask how many K-space bands can I obtain? Okay? And the way to do this is actually very simple and involves a kind of extension of what's called the K.P method. The K.P method is used by people to get nice plots around high symmetry points, but really what the K.P method is a nice method of subduction of a representation. So what you do is you go in the Brillouin zone at a high symmetry point, and you find that the Hamiltonian breaks into energies or wave functions that transform on the representations of that high symmetry point symmetry group. You go a little bit away from the high symmetry point, and you find that they split into representations of whatever line I've went away in the high symmetry, away from the high symmetry point. So here's how so now what you can do is you can map how bands connect in the Brillouin zone into a graph theory problem. Why? Well, let's just take this following example. Let's just take graphene and go from gamma to K. At gamma, I claim that graphene with pz orbitals has the following representations: gamma 8 and gamma 9. Okay, whatever. This is pz orbitals and spinful, so I have to have 4 bands because I have 2 bands at two orbitals at site A, 2 orbitals at site B, so 4 bands. So I have 2 representations at the gamma point, gamma 8 and gamma 9. These representations at the K point, these representations at the M point, whatever. Now the moral of the story is that I go away from the gamma point on this line, and I see how my representations break up. They break up into representations of the symmetry group of this line. But I can do the same thing from the K point. I can go away from here to here and see how my representations break up, and they transform into representations of the same line. Okay? And now the moral of the story is that I can connect these bands only if the representations match. Right? And this obviously is a graph theory problem. It tells you all the ways you can connect the bands in the Brillouin zone. And you can form adjacency matrices, etc. But it turns out that for graphene, with pz orbitals, there's 2 ways you can connect the bands in the Brillouin zone. First one is 4-fold connected, which is what Zach and Bakri and Michel were saying, that I have pz orbitals at high symmetry points in the Brillouin zone, at the high symmetry points in the lattice, at the A and B positions, pz orbitals spin up and down. I'll have 4 bands. I can obtain a connected elementary band representations. This together are an elementary band representation. But it turns out that you can have, in K space, this other band structure, which is disconnected. Okay? By virtue of it being disconnected, together they form, if I was to take these both together, they would form the same elementary band representation as this one. But by themselves, this is not an elementary band representation. This is not an elementary band representation, so this has to be topological. Okay? This type of structure has to be topological. And it's really why graphene, when people found graphene to be a topological insulator, it's really, there's nothing else they could have found. Graphene with pz orbitals at where they sit has got only 2 phases, gapless or topological. Okay? It doesn't, if in order to get something trivial, I would have to move the center of charge to the 1A position. But if my center of charge sits at the on the A and B sublattices, there's only 2 phases of graphene, and there's nothing else you could have found. Okay, so now all these are on the website. You can go check them, and you can see what you can ask if having some orbitals on some site of the lattice, if what they induce, if the band they induce can be topological or not, and that's given by this decomposable thing. Now, the last slide that I want to show is how to use this to obtain a new thing. So it turns out that I've talked about topological insulators as having surface states on surfaces when you terminate them. So that's a TI, it's got a surface state here. That's a quantum Hall effect, it's got an edge state here. But you can now define what's called a second order TI, which doesn't have surface states on surfaces, but it has hinge states when you make a hinge in the system. So this is kind of a extra bulk boundary correspondence. So normally the bulk boundary correspondence in high energy and condensed matter tells me I have a non-trivial bulk, which is topological, I get a surface state. Here I have a non-trivial bulk, I don't get a surface state, but I get a hinge state. So now the question is, do they exist? Okay? And using topological quantum chemistry, which is basically just getting a material and seeing if I can write it down as elementary band representation, we find that bismuth pure bismuth is a system that's topological. It's been predicted to be trivial for 10 years. Well, ever since, well, for not 10 years, many years, more than 10 years. But since people knew that the topological insulators exist, they predicted bismuth to be topologically trivial because it doesn't have surface states. But what it has...
But it's a metal, right?
Well, yeah. So this is when if you take the Fermi level to do this, right? So yeah. So you're right. It's a metal, but it does, it does something like this. Sorry. So if you took the Fermi level to do this, okay, yeah, indeed. But I'll show you the experiments where actually you can see them. So what turns out to happen in bismuth is that some set of symmetries, and using topological quantum chemistry we found which ones there are, allow not for surface states, but for hinge states, which are basically quantum spin Hall states that run on hinges. And if I make, for example, a hexagonal prism of bismuth, this is the structure of hinges that they'll run around. Okay? So now you can go to Ali Yazdani's lab and say, well, can I make these type of structures on a certain, can I make this type of structures? And he's going to say no, because they're not easy to make. But what you can make is you can grow terraces, hexagonal terraces on bismuth, or hexagonal dips on bismuth. Okay, and this is how they look, and you can clearly see the STM high resolution images where you see a high density of states here, here, and here, which is the same thing as here, here, and here. And you can have transport experiments that basically show the same type of hinge states. So there's a lot of topology that you can get with these materials. There's a lot of edge and hinge states, and there's a lot more to the bulk boundary correspondence than we can get. For example, this is a set of all the materials that you can predict with our method, and that's where the outlook of, well, part of my research is. Thank you so much.
Questions? Paul.
Let me start. If I was following this correctly, what you actually said was that the bands have to be an irreducible representation of the space group.
Atomic limit bands.
Now,
yes, atomic limit bands.
It's the atomic limit thing that I'm not getting, because of course the space group statement is we knew that.
Yes.
And
well, we didn't have it classified, but we knew it, the statement. Yes.
true.
Yeah.
And I don't know. I never understood Koster's tables. Maybe he classified it.
No, that's the very good point. So basically the moral of the story is that if I start with, so let's take the quantum Hall case, and take a fill band of the fill number. The question is, can I represent this fill band only in terms of maximally localized Wannier orbitals? And the answer is no. I'll always have an extended state. Right? So, and this extended state, as you know very well from Kalmer, Laughlin, etc., is just the extra. If you try to express it in terms of Gaussians, is the extra state. Is that there's a sum rule that. So this is the extension of that to all symmetries. So what you're saying. So now you say, can I express a quantum spin Hall state, a band that has a topological insulator state with time reversal, in terms of Wannier orbitals that are localized and that respect time reversal? And the answer is no. What I'll do is, if I try to impose time reversal on the Wannier orbitals, I'll find out that I have to have at least one Wannier orbital, or actually a Kramer's pairs of Wannier orbitals, that are delocalized.
Am I allowed to follow up?
Yeah, of course.
But is it clear?
Space is the group theory statement.
Yeah.
And of course, the group theory statement is kind of goofed up when you have edges, right? But the group theory statement that we know, and now you're adding something,
Right.
which is the atomicness.
That's right.
So you want to build up the space group starting from point group plus some rule of descent. And are you saying that some space groups cannot be built that way?
What I'm saying is, yes, what I'm saying is that some band structures in K-space. So notice that I was building, when I built...
All band structures are irreducible representations of space groups. So
in K-space.
correct.
The question is, if I have a K-space band structure that looks like this, I'm going to put my Fermi level here and work only with these states in this band and ask, can I represent these states in K-space, can I represent them in real space as maximally localized Vanni orbitals? So I'm having, these are states in K-space, I'm choosing some states in K-space, and I'm asking them, can I span the same basis of states that I span here in K-space, can I span them with maximally localized Vanni orbitals in real space? The answer, if this is a quantum Hall state, is no. And this is just the generalization of that to the full. So the answer is, if it's a quantum Hall state, I can certainly, this is a filled band that's got Hall conductance 1. It can never be expressed just in terms of maximally localized Vanni orbitals in real space. I'll always have to have an extended state, at least one extended one delocalized Vanni orbitals, which is my edge state. Yes. So this is the extension to. So quantum spin Hall would be, if this was a quantum spin Hall, I could not represent this band in terms of maximally localized Vanni orbitals. They respect time reversal symmetry. If this was another symmetry, I could not expect it. You just add the symmetry. So obviously, by building the atomic limits are built from orbitals that respect all the symmetries. So that's why they're atomic limits. Anything that's not an atomic limit has to be topological. So we classified all the atomic limits.
Okay, maybe we entertain one more question, Ron. Oh, two more, Steve and Ron.
Yeah, so if I've understood the construction, I take some set of bands and I can construct Wannier functions for these. And they'll have that's what you refer to as atomic orbitals, but I can think of them as Wannier functions for a set of bands,
yes,
which respect the appropriate symmetries.
Yes.
And then the question is, can I break those bands apart
yes,
into gap systems such that each subband can't be represented?
That's right. That's right, exactly. I mean, so I didn't go through it. There's several cases. So there's one case, like you said, can I break them apart? Or there's another case in which I take two of these bands represented by two different sets of orbitals, and I invert them, and I open them up again. Yeah. And then neither the lower part nor the upper part can. So there's several cases, but so there's, for example, graphene is a case where you can, you take one set of orbitals and you can split it, as you said. Yeah. Bismuth selenide is a case where I take, two sets of orbitals and I close the gap and I split it. I split it afterwards. So there's different.
Wannier functions for the whole set.
That's right.
And then I mess them up.
That's right. So graphene is this. So graphene is together is one elementary band representation in the sense that they come from one set of orbitals okay, but this one is not. Bismuth selenide is two sets of elementary band representations, but each one is not. But the point is, you can just now we're running a search on the full database, basically just trying to, there's about 10% of the materials are topological.
10% of all materials?
Yeah.
Oh, this news to me.
Well, of all insulators.
Okay.
Of
all insulators, Ronnie.
The really appealing part of the argument is this separability of some sets of bands that individually are not elementary band representations.
Right.
So would you judge the predictability of topological semimetals in the long run to have such a strong connection probably be not as easy as for insulators?
Yeah. So very good. So you can. It's actually similarly easy. You just have to add an extra term. So what you do. So for semimetals, what you would do is you'd have, something that looks like this, for example, right? And you'd say, well, I'm going to put my Fermi. I get a code. I get an output of the code, and I put my Fermi level somewhere here, right? And I look at, what these bands below this Fermi level does. But I don't know. I don't want to. I don't want to compute density of states, right? I don't want to compute anything that's not qualitative. So what I'll find out is that if I look at these bands below and try to match K-space, try to find a trajectory of these bands that's connecting K-space, I'll find out that I can't, because this band connects with this guy and this band connects with this guy. So you just have to add the extra thing that we've already done with the graph theory, the connectability in K-space. But this is something, so predicting semimetals is as easy as predicting, the only thing that you can't fully predict is anything in symmetry group 1, which is no symmetries, which you would still be able to predict it by doing Berry phase calculations. But when you have symmetries, anything that's imposed by symmetry, you'd be able to predict.
Maybe last question.
So how did you get rid of all K-theory indices and topological invariants in general?
Just because I don't know K-theory, so, so I got rid of them by necessity, by ignorance and necessity, and also because K-theory never predicted any material. So this is kind of a way to, so out of this you can get the K-theory indices, and there's a very easy way of getting the K-theory indices. These elementary band representations are just the atomic limits, but these things here, these things are called compatibility relations. They tell you how a representation at a high symmetry point in the Brillouin zone breaks up into others. Now, what you can do out of this is you can build what's called compatibility matrices, which are basically these graph matrices. And what you can do from this is you can run a Smith normal form on these matrices. Is basically solving the compatibility relations in, you want to solve them in integers, and the real reason why you want to solve them in integers is because you cannot have half of a representation at a high symmetry point, and that Smith normal form in the end will give you the same indices that K-theory gives you. There's a way of getting from elementary band representations to indices, but elementary band representations are far more useful because they actually allow you to find this, whereas K-theory just gives you a bunch of indices. But the two, you can go from one to the other.
Okay, let's thank Andrei again.